Hello everyone. This chapter is an introduction to computing network standards. We'll first talk about some of the history of the internet, and then we'll introduce what is network standard, and then we'll talk about the importance of message ordering. Also, we'll give some example of message syntax, and then we'll talk about how we encode application messages, and finally we'll introduce what is the meaning of vertical communication on host. This diagram is showing the early ARPANET. So the ARPANET was kind of like a research project that's sponsored by the military in the US. So ARPA actually is the Advanced Research Project Agency, which is actually under the Department of Defense in the US. So in the very beginning, they actually tried to provide some research funding on how computers can communicate with each other for military purpose. So there are some universities participating in the beginning, University of Utah. This one is University of California in Santa Barbara, and so on. So of course, at that time, these computers at different sites were connected by some very slow connection line. So it's like say 50 kilobit per second line, and this one is UCLA, right? University of California at Los Angeles. So they have these different IMP, that is the interface message processor. So these are computing devices that are responsible for handling the message. So it's kind of just like the switch or router these days, right? It's just kind of the network devices. But of course, at the time, the computers were very big. So even these devices were very big devices. Anyway, so the computers, so like the host here, are connected to this IMP, and the IMP connect to each other, and then through this IMP, then they can kind of communicate with each other. So there is a company called Bolt, Beranek, and Newman that designed the IMPs. But at that time, there were no standards for the application programs or protocols for the host to communicate with each other. So basically, what they could do is to send messages, but then there were no standards on how the messages should be formatted or how they should be handled. So therefore, an informal group was formed to create the needed standards. So they call this the Network Working Group, the NWG in short. So the group consists of mostly engineers and some graduate students. So we had no formal standing. So they call their standards request for comments or RFCs instead of standards. So they kind of try to be humble. So they set a set of standards, and they basically they were saying they were asking for comments, but many of these RFCs are actually standards that have been adopted by the different companies and organizations. So when you look for networking standards, you will see a document called RFC, which you may think is a draft, but actually many of these RFCs are not draft standards, they are already the standards. So this network working group is kind of informal and egalitarian, so they are working on rough consensus rather than voting. So they have designed many simple standards based on the running code, which are quick and inexpensive to implement because they want to allow faster adoption and also faster implementation. So later on, this working group emerged into the Internet Engineering Task Force, which we have talked about last time. Is one of the most important standard setting organization for the internet. So the Internet Engineering Task Force actually kept many of the characteristics of the working group. Okay, so now we are going to give an introduction to network standards. So network standards actually cover message semantics, syntax, order, reliability, and connection orientation. So sometimes people call it protocols. So, so standards and protocols are more or less the same thing. But protocols, I think, is a particular type of standards that talk about how we should do things. So it's not a standards for a product, but kind of a standard for some processes. So that's protocols. So I think when people talk about network standards or network protocols, I think more or less they are talking about the same thing. So there are different things that are defined in network standards, like message semantics, so the meaning of the message syntax, kind of the grammar or the format of your message, the ordering of your message, and reliability of your message. So in networking, reliability has a special meaning. When we say protocol is reliable, that means you will try to make sure that a message is delivered correctly and successfully. So that means after a message is sent, I will need to wait for acknowledgement, saying the message has been received by the recipient. If it is not received, that means if I did not get the acknowledgement, I will try to resend the message again. So I try to ensure that the message has arrived the recipient successfully. So in that sense, we say it is reliable. If we say a protocol is not reliable, we are actually not saying that this protocol is not good, is a bad protocol. When we say a protocol is not reliable or it kind of is unreliable, we are saying that we are just saying that it does not have a mechanism of checking the successful delivery of the message. Right? So we are not saying a unreliable protocol is bad. It's just one of the property. And then the last one is about connection orientation. So this is about whether a connection is to be established before you send a message. If there is such connection establishment, we say it connection oriented. If there is no connection, that means you just throw a message there without like establishing a connection, then we call it a connectionless protocol. So later on in our course, we will look at the different protocols, and then we will see like which of them are reliable or unreliable, and also connectionless or connection oriented. In this chapter, we will also look at some of them. So when we have standards, we can have interoperability among vendors. So as long as everyone is following the standards, you can have different companies to manufacture the different networking devices. You can have also different software companies to write different programs, different drivers based on the networking standards, rather than having one or two big companies to write all the software or to produce all the hardware. So when you have this, you actually have a lot of competition among the different companies, like hardware and software companies. So if you study economics, you know when you have competition, actually the price will be lower, and also encourages growth in functionalities. Right? You either compete with price or you compete with better quality of your product. So when you have competition, actually um, it has driven up the quality and also driven down the price a lot especially in the early days of the internet. This diagram shows a recap of the first three layers that we talked about last time. So remember, the physical link is the connection between two adjacent computers. And usually when we talk about the physical layer, we're really talking about the physical medium that the message is passing through, like the cable or the Wi-Fi signal. When we talk about the data link, then it is about the layer 2, and this is usually about the transmission of message within the simple network, or within what we call the single network, right? So then you may have multiple switches, but then and then you can have multiple hosts, and then these are within one single network. Then again, one example is your home network, or it could be the network within an organization. And then router is the one that you put at the boundary between multiple, or the connection or the interface between multiple networks, right? So this one is one single network, and this one is another single network, right? From router 1 to router 2, and this router 2, and also the switches Z1, Z2, and also host B, and this one is another single network. Then if we talk about the whole path from host A to host B, passing through multiple networks, then we call this one a route. And this one is at the level 3, and it's also like the important part of the internet, like how different networks can connect to each other, right? So that's why it's called internet. It's the inter-network communications, because we have multiple single networks here. And then on top of the first 3 layers, we also have layer 4 and layer 5. And layer 4 is what we call the transport layer. So it's actually about the host-to-host communication. When we are really looking at the two hosts, or the two computers or devices, then how they are handling the communication. And finally, when we go to layer 5, then that's the application layer. So it's really about the application programs that you are using. Maybe it's about web browsing, then you are having the HTTP standard. If you are using email, then it's the email standard. When you are talking about like say WhatsApp, then you have the WhatsApp or some of the message communication standards that you are using. So there are many different types of application standards. But then for transport layer standard, then it's mostly TCP and UDP, right? These are the two most popular standards. And then in the internet layer, then it's mostly about IP, right? The internet or internet networking protocol. Right? So just a quick recap of the 5 layers. So layer 5 is the application layer. So it um, governs how two applications work with each other, even if they are from different vendors. Whereas, you know, like the web browser can be Chrome, can be Internet Explorer or Internet Edge, right? Or it can be some other browsers that are from different companies. And then we're talking about the web server. Again, the web server can be built by different companies. Can be Apache web server, can be your Microsoft web server or other web servers. So as long as they follow the same standard, then they can work with each other. Then layer 4 is about the transport layer. So it's actually governing the aspects of end-to-end communication between two end hosts that are not handled by the internet layer. So it actually taking care of stuff that are not handled by internet layer. So what are these stuff that are not handled by internet layer? So it is actually about some of the reliability issues, for example, and then another one is about the connection issues. So later on when we talk about the transport layer, we'll talk more about this. And then layer 3 is the internet layer. So it's actually about the transmission of packets across an internet. So typically by sending them through several routers along the route. So as we said, because the message is passing through multiple networks. So the router is the interface between different networks. Right? So the internet layer actually is about how we can successfully pass the message from one host to another host through the different routers. So which route should be taken, which router, that means I should forward the message to such that it can arrive at the recipient successfully. So it also covers packet syntax and actually a little bit of reliability, but not too much. Most of the reliability actually are handled at layer 4. So Layer 2 is a data link layer. So it's about the transmission of frames across a single network. So as we said, data link is just about one single network. So usually it's about by sending the frames through several switches along the data link. So of course it also governs the frame syntax and reliability at this layer. Right. So as we said, the message at layer 2 is called a frame, right? So it's not called packet. When we are talking about packet, that is about level 3. But when we talk about frame, that is about level 2. Right? And then the devices are called the switches. They are still within the same network. But again, still it's similar to router in the sense that it also need to decide which switch I should send the message to. Right? And then finally, at the lowest layer is the physical layer. So it's the transmission between adjacent devices connected by a transmission medium. So it's about adjacent devices. So the physical layer will not worry about going through multiple devices. It's just between two devices. Like it could be two computers, but a lot of times it's about one computer and one device or two devices, network devices, right? So again, it can be just a LAN cable, it can be optic fiber, it can be Wi-Fi, it can be your mobile phone signal, and so on. This subsection looks at message ordering. So if you take HTTP request response cycle as an example, when someone wants to browse a web page, so you go to the web browser, you type in the URL, then your browser actually will send an HTTP request message to the web server program. Right? So the client must initiate the message, and then the web server program will respond with an HTTP response message with the web page requested or with a 404 file not find message, right? So you will send a message back to the client, but there is the particular order here, right? So the web server program may not transmit any message until it receives an HTTP request message. Right? So that's kind of the order of the message, and it's defined in the protocol. So different programs or different protocols will have different message order. So this HTTP request response cycle is one example. And the second example here is a TCP session. So the protocol at layer 4. So when I need to start a communication, so if host A wants to start a communication or a connection with host B, it will first need to send a sync message. So right from this message from A to B, right? So that means I want to start a session, and then B will respond by this message, which is an acknowledgement of the same message. The acknowledgement is basically just saying, I received your message, right? And then A will have to send another message, which is the acknowledgement of the acknowledgement. Right? So I acknowledge that I have received your acknowledgement. Right? So I have to send another message to B. So this is what we call a three-way open in a TCP session. So it's just kind of like when you need to call someone, you first dial the number, and then the other side, when they pick up the phone, they will say hello, and then you also say hello, right? So this one is kind of like a informal protocol to start a phone conversation. And then in TCP, then you have to follow this message order also in order to start a session. So we call this a three-way open. So and after opening, then you can send a message like this. Then I can send my data to B. So in this case, it could be like if we use the HTTP example before, so then your HTTP request like is packaged as a message here, then it's sent to B. Then B will acknowledge. So it's just saying I have received your request. So that's the acknowledgement. and then B will do the processing. It will try to retrieve the web page from the web server, from the file, and then it will package it in a HTTP response, and then this response message will be sent back to A. Right? And then after A has received this message, A will also send acknowledgement. Right? So we assume there's no error, so this is what will happen. So then maybe A will further send more HTTP requests, and in this case there may be an error, right? There is a transmission error, and B did not receive the message. So and the host A will wait for a while, and there is no acknowledgement from B, right? So there's no acknowledgement, so A will actually send a message again to retransmit it. So that's actually the property of TCP, making it reliable. So that means it will make sure if a message is not acknowledged, then it will retransmit it again. And okay, so now this time there's no error, so B will respond with an acknowledgement, and then B will also retrieve the web page and then send it back with another HTTP response, and then A will acknowledge the receipt of this response. And so that's how TCP works. So if the connection is over, so now A wants to close the connection. So A will send this message like fin, so it means finish or final, right? So basically send a fin message to B, and then B will acknowledge this fin message. But then B still has something to say. It still have a message to send. So B will further send this message. And then A will acknowledge the receipt of this message. So even A has sent the fin, so it only means that A does not want to send anything anymore, but still B can still send something. So B will still send the data here, and A can still receive this message and send acknowledgement. So now B also has finished talking. So B will also send a fin here to A, and then A will acknowledge receiving this. Then now both of them have sent the fin that they have both said goodbye. Then they can both hang up the phone. So that's what they call a normal four-way close in a TCP session. So again, as you can see, so all these have defined order, right, in the messages that can be sent and handled. So some protocols define the order. For some other protocols, then you don't need to worry too much about the order, right? Now most of the protocols actually there's some sort of order of the messages that should be followed. So just a quick comparison of the two protocols that we look at. So HTTP is what we call connectionless protocol. So that means the two programs, like the two hosts, like the web server and the web client, they did not establish a fixed connection there. Right, so the connection actually is handled at the layer 4, handled by TCP. And then in HTTP, there is no particular opening, closing of the sessions, right, of the connection, because it's connectionless. And then of course in TCP, there's opening and closing. But then in HTTP, there's also no acknowledgement of the particular message. So that's why it's not what we call the reliable protocol. So here it says it's unreliable. But again, it doesn't mean it's bad. It's just the property of not having acknowledgement and retransmission. And then TCP, we have acknowledgement. But you see, actually, there are a lot of acknowledgements taking place in TCP. So actually all these acknowledgement messages place a very heavy load on the network because there are so many types of communications. So and also because of this acknowledgement, we say that TCP is a reliable protocol, and HTTP, as you say, is unreliable. But because all these different layers work together, actually we don't need all the layers to be reliable. If we do the checking at every layer, then that would be actually create even more traffic on the network. So that's why a lot of times people just rely on um, especially on the TCP layer that to deal with the reliability. So now we'll look at message syntax. So a general message organization looks like this diagram. Here we have a message with three parts. Like this one is the data field, so the actual data that you want to send. And then this one is the header, so what information we want to add at the beginning of the data. So in the slides orientation, which is following the textbook, actually what we have is here on the right hand side is the beginning of the message. Right, so that's the beginning of the message. So when you send a message, like this one is the first bit, second bit, third bit, and so on. So that's how the way they write it. So that's why the header is on the right hand side instead of the left hand side. And then here is the data field. And then some messages will have what we call a trailer. So that means information that you add at the end of the data. So usually in the header field, we have things like address where you want to send this message to, and then you also have other header field, for example the version of the protocol, whether there are any particular things you want to pay attention to, and sometimes it could be the size of the data field and so on. So later on when we talk about the different protocols, we will talk about some of the header fields in some of the protocols like IP and TCP. So there are also some messages that do not have a trailer, so it's only the header and data field. So this is also very common, right? Because normally you just get all the metadata or header information from the beginning. You don't need to get it from the end. Yeah, but for some messages, we do have to get it from the end. So it actually depends on the protocol, but both of them are um, like something that we will see later on in this course. So sometimes you may have messages like this. It's just a message with only the header. There's no actual message. So there's nothing here. It's just some header information. So a lot of times like this kind of message is kind of some message for administration. For example, sending some acknowledgement or sending some kind of error messages or for error message and so on. So later on, we'll also see a few examples of things like this. This slide shows an example of an Ethernet frame. So we look at the message syntax. So if we talk about frame, then we know it is at layer 2, right? Because frame is the message, the name for message at layer 2. If we talk about packet, then it's layer 3. If we talk about segment, it's layer 4. Right, but frame is layer 2. I know like if you are not familiar with these terms, you may be confused in the beginning, but after a few chapters, probably you'll get more familiar with this term, then you will remember. Like frame is layer 2, packet is layer 3, and segment is for layer 4. But they are all messages. So based on the definition of the protocol, so we know that the first 48 bits here of an Ethernet frame is the destination address. So it's where you want to send a message to. So it's based on it's in the format of EUI48 address, which is essentially a MAC address. And then we have another 48 bits, which is the source address. So your own address, like who is sending out this frame. Again, 48 bits. And then we have some other optional header information like the tag protocol ID and the tag control information. So these are 2 octets each, and also the length is also 2 octets each. So octet is actually 8 bits, like like the prefix oct, right? Like octagon, octopus, then it means 8. So an octet it just means 8 bits. So 2 octets actually means 16 bits, right? So you specify the length of your actual data content and so on. So in Ethernet frame syntax, fields are listed in order. Each is a certain number of octets long. So octets 8 bits, right? So basically it's a byte, right? Okay, and then you also have the data field here, which you have some subheader, which is a logical link control. And then most importantly, you have the actual message that you want to send here, the actual data. So this one is actually the packet. So it's the pack. So why we call it packet here? Because it's what we have at layer 3. Like, so you will have the IP header. So it's the whole IP packet, like including the IP address, source address, destination address for that particular message. So if you look at this part, you can think about your actual message is actually the application message, right? It can be HTTP message, and then you kind of break it down into a TCP messages. Right? You break it down into fragments, and then you package them into TCP packets. So it's kind of like you put it into an envelope based on TCP form requirement, and then you put the TCP message into the IP format. So you put it into another bigger envelope, and then you write the IP address on that envelope. And this one is the kind of the envelope with the data based on the IP requirement. And then what you are doing here now is actually you have this IP envelope, or in networking terms is your encapsulated message. But then you put, what you are doing is we put this envelope into an even bigger envelope, right? So this one is an even bigger one, right? So the bigger envelope is like based on the Ethernet, based on layer 2 requirement. So that's why we have layers of encapsulation. Like for each layer, you add something. This one is how you add things like to your layer 3 message based on your layer 2 requirements. Right? So that's why your message will become longer and longer when it goes through the different layers. Right? So that's the actual data. After the data part, there is the frame track sequence. So this one is actually the trailer of the Ethernet frame. So the frame track sequence is a checksum to make sure that the message received by the receiver is basically correct, so it has not been changed. So usually there is a calculation that can be computed by the sender and also by the receiver based on the data, right, or based on the whole frame. And if the final result is the same, so that means that message has been sent without any errors. So if the two frame track sequence are different, then that means, or if kind of the calculation is not correct at the end, then the recipient will know that there is some error in the transmission. So this is an example of the TCP segment and the UDP datagram. So we said normally we call it segment at level 4, but actually, or layer 4, but actually it also depends on the protocol. We know TCP is most popular, right? But in recent years, we know a lot of applications are using UDP, and then usually in UDP we don't call it segment, we call it a datagram. So the main difference between TCP and UDP is that UDP is what we call unreliable. So that means, as you said earlier, when we use UDP to send a message, we do not worry about acknowledgement. So that means we do not need to wait for the receiver to tell me they have received the message. We will just keep sending the messages. So normally UDP is more suitable for video streaming, for example, when you have errors, right? Sometimes you have one or two errors in your video, that's fine, right? We are just going to skip it. If you do all the error checking, right, for your video, that is going to be very slow, right? So when we do streaming, on some other applications, we may use UDP. But for the more traditional, like web applications or internet applications like the web, like email, then we use TCP. Right. So this one, we will talk more about the differences between the two later. But we look at this diagram, we just first look at how a TCP segment looks like. And so in the beginning, we have the source port number, 16 bits, and the destination port number, which is also 16 bits. And then we have 32 bits, which is the sequence number of your TCP segment. Because remember we said an application message usually is broken down into fragments, and these fragments are being sent individually. Right? So when these segments are being sent from say host A to host B, they may not arrive in the same order. Just like again when you have a pile of letters, if you want to go to mail them at the post office, they may not arrive at the recipient in the same order. They may arrive in different orders, right? Or just like imagine when you are sending emails to your friends, like sometimes like normally they may arrive in the order that you sent, but sometimes they don't, right? Sometimes they arrive in the kind of different orders. So the sequence number actually keep track of which message is the first message, which message is the second message, and so on. So there is a sequence for each message. And then we also have the acknowledgement number, so which sequence you are actually acknowledging when you send the acknowledgement. So that's kind of the meaning of these two. And then we also have some other information like the header length and some bits reserved. And there's also a flag field in TCP segment. So these are like 1 bit fields. Then if the value is 1, then that means this field is this value is set. If it is 0, then it's not set. So some example of the flag fields are like the sing, acknowledgement, or the fin, and there are 3 others, right? So that means if the sing field is 1, then that means it's a sing message. If it's 0, then that means it's not, right? And then there is the checksum. So just like the checksum we look at for the Ethernet frame. And then there are some other header information, and sometimes like your header information may not be kind of using all the 32 bits, right? Or sometimes not kind of like nicely aligned, so sometimes you may have to do some padding. That means you add some 0 at the end to make sure that it fills the whole byte, or it fills the whole 4 bytes, right? And then after all this header, then you have your actual data here. And this example is the UDP datagram. So it's actually much simpler. You just have the source port number, destination port number, and then you have the UDP link, and then you have the checksum, and then you have the data field. So we are not doing, again, for UDP, the most important thing is much simpler, and also it does not do the acknowledgement and also the retransmission. So in general, it's much faster, but of course, it is not reliable, as we said. So again, we'll talk more about the difference between TCP and UDP later on. So in both TCP and UDP, we saw the port number. So actually, the mechanism of using port number is something important for multitasking servers, and also actually to decide which applications should receive the message. So for example, a packet containing a TCP segment with destination port number 80 is being sent to the IP address of this server. Right? At the IP level, we only know the IP address. So it's actually passed to this server. But after it's passed to this server, then the server will need to know which program should handle this message, right? So that's actually is done by the port number. So normally the different applications will be running on different ports, right? So these are not actual port where you can plug a cable in, but these are the virtual ports, right? So for example, SMTP run on port 25, and HTTP runs on port 80, FTP runs on ports 20 and 21. So multitasking servers actually run multiple applications on one server, right? and each is associated with a port number. Then when the message arrives, I will know which application will handle this message. So for client, actually we use the ephemeral, that means kind of temporary port numbers. So usually they are in the range of 1024 to 4999. So a new ephemeral port number is used for each connection. So when you try to connect to the web, so the client does not use port 80, right? Because that's actually for incoming traffic. They are reserved for the server applications. So usually the clients will use this range, and the server usually will use like from 0 to 1023. But of course, we know like some other servers will use other port number, because 0 to 1023 are already used by a lot of well-known server programs. So when you have some new programs, you may have to find some new port numbers to use. Like for example, like say Tomcat, like for Java servlets, like people will use, then it has to use the port 8080, right? Then when you build a new protocols or new applications, then you may have to think about a new port to use. But anyway, so for the common ones like web server, we know the standard one is port 80, then these are used by the servers. So when the client again wants to get to a web server to request for a web page, then a socket is actually established. So a socket basically is a connection from one host to another based on TCP. So we call it a socket. So the socket consists of the IP address and also the port number. So this one is the IP address and port number of the source. This one is the same for the destination. And then when it's going the other way, then it's the opposite, right? So the source is this web server at port 80, and the destination is the IP address of the client and the port number of the client. So we call them the sockets, and then all the communications and messages can be sent through the sockets. So this is just another example showing the same client if it's also using email at the same time. So the client also needs to connect to the SMTP server. Then there will be another socket that is being established here, with the destination being the web server and also at the port 25. So and then of course like this time the client will use a different temporary port number. So that's why when the client is receiving the web page from the web, it's going to another port, and is receiving the message from the email, then it is using like this port. Then again, the client computer then will be able to know when the message arrives, which program should handle the message. So for the connection going from the mail server to the client, then for this socket, what would be the source IP address and port? What would be the IP address and also port number for the destination? So this one is leave it. We'll leave it to yourself, so you can try to fill that in. So now we'll look at the HTTP message syntax. So we know layer 5 is the highest layer, so it's the application layer. So it has more standards than at any other level, for any other layers, because we have so many different applications like web browsing, email, FTP, messaging, and so on. So there are many different standards that different companies, different people have developed. So of course then HTTP is not the only application layer standard, it's just one of many existing. We have just been using HTTP as an example because it's kind of one of the most popular use of the internet. So there are many different application layer protocols such as SMTP for email, and some of them are much more complex than HTTP. So HTTP actually is relatively simple. So if we want to get the content of a web page, so we send an HTTP request message. So for example, get, so it's the action that you want to do, and this one is the page that you want to get, and this one is the protocol of HTTP that you are following. So it can be 1.0 or 1.1. So this one is just a line feed, so it's new line character. And then this one is the host, so where you want to get the page from, so it's the web server that you are connecting to. And then what is the connection type, so you can keep the connection alive or you don't keep the connection. So this one is actually kind of asking the TCP to how to handle the connection, whether you should keep it open or just close it every time. And then after the web server receive an HTTP request, then you will again get the web page from the hard disk, the one requested by the user, and then package it into a response message. So the response message may be something like this: HTTP 1.1. So that again, this syntax is defined by the protocol. So in the beginning, I just put the protocol version, and then this one is the status code. So 200 means okay. So this one is a status message. So some other status codes, like probably you have seen before. Right? The most popular one is definitely 404. I found not found. And then you have a timestamp, and then you have the server. This could be the name of your server software. It could be like Apache. It could be other server. And the mine version. So in this case 1.0. And then your content type, so it's text plain, so it can be other things. It can be sending back an image in JPEG format and so on. And then you have two line feed here, and then you have the file to be downloaded. Again, it can be an HTML page, just text contents. It can be graphics, sound, or video. But anyway, so here you put the actual content of the page or the resources that the user requests. So HTTP actually is a relatively old feeling protocol. So if you know that HTTP was developed kind of in the late 80s, around 1989, right? So before that, the internet has been around for 20 years, but people have been using it only for like email, news group, that are mostly not web based, right? There was no web before 1989, so it was like most of them were console based, right? And then they were also not using the web protocol. They were using their respective like SMTP or other news group protocol or IRC type of thing. But then 30 years ago, then someone like Tim Berners-Lee, right, developed the HTTP protocol and also HTML standard. So if we look at it now, it's already a like rather old protocol. Right? So it's actually based on email protocol, which is even older. So actually it was developed for rapid development, so it was easy to understand. Like people could build web browser, web server easy, but it was actually not very efficient. As you see, like for example, the fields were um were ending with the line feed character, like carriage return line feed, right? CRLF, which actually starts a new line. But actually, if you think about it, it's wasting some space, right? You can just use one special character to take care of that, right? Sometimes, one or two special characters or other things, and also like those like HTTP 1.1, like the header information we saw, they are not in bits or bytes. They are actually in characters one by one. So it's also wasting a lot of space, right? So it's relatively old, but because it is so popular, so and also nowadays there are so many software packages, so many applications are running on this protocol, so it's also rather difficult to change, right? But of course, people have already been they have been talking about like an update to HTTP for a very long time. Right, so now we'll talk about how we do encoding of your application messages. We know computers handle data in bits like zeros and ones, and also send data over the network also as bits. So when we have some text or some other data, so how do we convert them to bits? So this is kind of basic computer stuff. So some of you, if you already are very familiar with this, you can skip this quickly. So basically, for say letters or numbers or some punctuations, we actually have a standard called the ASCII standard. So we can just convert them into ASCII code. So each letter has a predefined value in ASCII. So we just convert it into ASCII code. And then some of you may ask, well, how about Chinese character or Japanese character? So usually for those, we also have something called the Unicode. So nowadays it's actually very common. So many applications handle Unicode. So basically it's just another mapping table for each Chinese character or Japanese character. You can map it to a Unicode. So it has the corresponding bit values that you can use. And then so if you are not familiar with binary numbers, so this one is like how you convert binary number to decimal numbers. So you know in decimal numbers, you will have a number like 503. This one is kind of the ones place. This one is the 10 place. This one is the 100 place. So 503 actually means 500 plus 0 times 10 times 10 plus 3 times 1. So it's actually 503 in the decimal representation. So for binary number, if we see a binary number like 01010, actually this one has the value of 1. This one has the value of 2, right? 2 to the power 1. This one has the value of 4, 2 to the power of 2. This one has the value of 8. This digit has the value of 16. So you just add them together, right? This one actually equals 1 plus 1 times 8 plus this one is 0 and then plus 1 times 2 and plus 0. So if you have 1010, this one when you convert to decimal is just 10. So you can convert numbers to binary and transmit it in the network, and then the receiver can also convert it back. So these are just examples of how you can encode a decimal number in binary. So probably many of you have learned that before, but we just do it quickly here. So suppose you have a decimal number 11. So if we want to convert it into a 4-digit binary number, so basically just 4 bits. So you first see whether the first bit here should be 1 or 0. So if this number 11 is greater than 8, so then this one should be 1. And then you take the difference 3, and then you see whether this number 3 is greater than 4. So in this case 3 is not greater than 4, so it's 0. But 3 is greater than 2, right? So this one should be it has a digit 1, right? So this one actually I think it's a typo here. It should be 3 minus 2 equals 1, right? And so this one will have the value of we have the difference of 1, and then so this one will also be 1. And then at the end, so because 1 minus 1 is 0, so you basically finish the conversion. So the final binary number is 1011. Sometimes you may have values that have different alternatives. Then in that case, you can also use bits to represent. For example, for the simplest cases, you have a variable that it can be yes or no, or male or female. So you can actually use just 1 bit to represent that, right? 0 for no, 1 for yes, or something like that. So of course you can also say some people use y for yes, n for 0. But the thing about it, you use y for n, y for yes, then actually y, this character is like it will be converted to ASCII, right? Then it will take 1 byte, it will take 8 bits, right? So then now you just use a single bit, then you are saving your transmission space and transmission like data loading or your storage space by 8 times, right? So a lot of times use bits to represent this kind of alternative is much more efficient. So that's why earlier when we talk about HTTP, we are saying the storage or the way that the message is structured is not very efficient, just like SMTP. So if you have 2 bits, then actually because 2 to the power 2 is 4, right? Because each digit has 2 possible values, then 2 times 2, you have 4 possible bit sequences like 00011011. Then you can use it to represent 4 different values, for example, directions like north, south, east, west, or 4 different colors. And then if you have 4 bits, you can actually use it to represent 16 possible different values. It can be 00000001, 0010, 0011, and so on. So for example, if I want to store like use these numbers to represent the top 10 security threats, right? So there are 10 different possible values. So if I use 3 bits, then it can only store 8 alternatives. It can only represent 8 alternatives, so that's not enough. Then I can actually have 4 bits. I need to have at least 4 bits, then 2 to the power 16. Then in that case, if I just use it to represent 10 different alternatives, that's also fine. Then it only means like 6 values will be unused. And how about like 2 to the power 8? If you have 8 bits, then you have 256 different possibility. So one example is actually the representation of color. So 1 byte per color will give you 256 possible colors levels. So in a lot of computer programs, especially the early days ones, actually what we have is we have the RGB representation. Then the value of R, which is the red color, can be from 0 to 255. So that's 8 bits. And the level of G, green color, is also the same, 0 to 255. And then B, blue color, also the same. Then that means together we only need 24 bits, right? 8 bits for red, 8 bits for green, 8 bits for blue. Then for 24 bits, we can represent actually many different possible colors, right? Because we have all the different levels available, right? You already have 2 to a power 24 different types of colors that you can represent. If you have 16 bits, then you can represent even more alternatives, right? 2 to the power 16 is 65,000. Then, for example, instead of just using 1 byte per color, you can use 2 bytes per color. And it will give you 65,000 color levels, right? So that will make your color even richer. And then how about if you have 32 bits, then 2 to the power 32 will be 4 billion, right? So for example, in the IP address, actually in version 4 IP address, 32 bits were allocated for the IP address. And so at that time, 50 years ago, people thought like 4 billion IP addresses would be much more than enough. But of course, nowadays we know it's actually not enough. So that's why people are coming up with IP version 6, which we will talk about later. So if we want to transmit voice, then how do we do that? Then usually like we use the microphone that will convert the human voice into analog electrical signals. So that's what microphone has been doing, right? To turn your voice into electrical signal. Just like people have been doing with telephone for more than 100 years. Right? But the electrical signal are not the digital signal. So we have to go through another process called the codec. So the codec will convert the analog electrical signals into digital transmission signals, or it can also do it the other way. So codec actually is basically standing for coder decoder, so you can do it either way. So you can change it into binary signals based on the magnitude of these analog signals, right? And then these binary signals are just bits, right? So they can be sent through the network. So finally, we'll talk about the concept of vertical communication on hosts. That means on each computer or device in the network. So we know like when we want to send a message, we are actually first starting with your application message, and I'm trying to get a web page from a web server, right? So I have my HTTP request message. So that's my message at the application level. So if I want to send this message to the web server, so I first need to break it down. If it's too large, right, I break it down into multiple segments. Then I pass it to the next level at the transport layer. Then the transport layer actually will take the HTTP message and then you will encapsulate it using the header of the TCP layer. Right, so if I have the remember the port information or some other TCP header information, I'll need to add them here. Then I'll pass it to the next level, pass it to the internet layer. So the internet layer actually will take the message from the TCP layer and then you add more header. So this time I will add the IP header, which includes the IP address of the destination, my own IP address, and also some other header information that is specific for this layer. So in this case, we encapsulate the TCP segment in the data field of an IP packet. Yeah, so the whole thing will come, this whole segment will become the data, or sometimes we call it the payload of this IP message or IP packet. So this whole thing is the IP packet. And the whole IP packet will then be passed to the data link layer, right, the layer 2. And layer 2 will add the header and the trailer. So it will add these based on the Ethernet protocol, and then it will become a frame. So we encapsulate the IP packet as an Ethernet frame. So you can see your original message, your original HTTP message is becoming longer and longer based on the addition of headers at different levels. So now it becomes a very long message, or in the analogy that we talk about, so now it becomes a message that is being stored in multiple layers of envelopes. Right? The whole Ethernet frame will now be passed to the layer 1, the physical layer. Then the physical layer actually will take care of the conversion of the bits, that is the whole message here, the whole frame here, into outgoing signals. So it can be electrical signals through your LAN cable, or it can be some Wi-Fi signal that you are going to send to your wireless access point. So that's what we call vertical communication on the source host. That when the message is received by the destination, then you expect the reverse of this process will be carried out, right? So the recipient will actually take away the even the header. So it basically is taking all the envelopes out of the bigger envelopes one by one, right? So we will open the biggest envelope, like open the Ethernet message and then remove the Ethernet header, and then you will remove the IP header, and then you will also remove the TCP header, right? And then finally the web server, the web application the web server program on the destination will look at the HTTP message. So of course, like in between, there are also some other things that will happen. For example, actually someone might open the envelope like with during the network. Like for example, if we are talking about the Ethernet frame header, the Ethernet header actually is only used within your single network. When it's going to through other networks going to the destination, your Ethernet header actually will also be changed. So what is being received by the receiver is not exactly the same as this one, right? But like as we said, that even the header will be replaced multiple times. But anyway, so when it's received, the format is still kind of something like this. And then as we said, the recipient has to kind of look at the kind of unlayer the message in order to get the final message. So that's what we call kind of the layered or vertical communication. So just a quick recap of all the protocols that we have looked at in this chapter. So at layer 5, we have looked at the HTTP protocol. So it's connectionless and unreliable. At layer 4, we have looked at TCP. So it's connection oriented and it's reliable. And layer 4, we have also briefly looked at UDP, which is connectionless and unreliable. But as we said, it's much faster. And then for level 3, we have looked, or layer 3, we have looked at the IP protocol. So it's connectionless, unreliable. Also, layer 2, we have looked at the Ethernet protocol, which is also connectionless and unreliable. Okay, so that's all we want to cover in this chapter. Thank you.